So guys, you ready for this? This is kind of fun. So this paper that you have in front of you that says gas laws homework, this is your homework packet for this unit. You'll notice there's no staple, right? So it's two-sided, but don't do too much, because I know we're creatures of habit. I should have wrote a 1 up here and a 2 up here. Go ahead and do that if that's helpful for you. Guys, the assignment today is going to be 1 through 13 on the front of this sheet, and then the homework that you're not going to see until well into May, because we've got labs to do, videos to watch, and SAGE tests to take. Oh, by the way, I forgot to mention to you, Friday in class, when you guys are gone, I didn't tell you about this, did I? During class on Friday, for those of you that will be here, we're going to spend the whole day reviewing for the SAGE test, just like you'd be doing at home. I'll crack open the laptops, and you can work in groups, and just like I mentioned to you, you should be doing at home. Guys, you'll have an uninterrupted 75-minute period to do more SAGE review. So that's what we're going to do Friday. So anyway, guys, this is today's homework right here. Wait, no, this is today's homework right here. Guys, this is the last homework assignment of the year. That'll be later in May. Now, while we're mentioning that, let me mention to you as well, guys, I'm completely up to date in my grades. But not only have I graded everything, but guys, if you take a look in Skyward, not now, but if you take a look in Skyward, you'll notice that I've populated Skyward with categories for everything we're going to do for the rest of the year. We've got 2 homework assignments, 3 labs, and frighteningly, 2 tests. So guys, it's all in Skyward. All the categories are there. You've got everything that you need to know. So that's the homework for today. So guys, what's this other page that I gave you? Some of you are going to be kicking yourself in the butt in just a minute. Guys, I was laying there last night, not able to sleep, thinking about everything that we had to get done today. And it dawned on me that maybe what I could do to make today go better was to print your class notes for you. So I printed your class notes for you. Some of you are going to, after today's over, go, wow, that really made learning a whole lot easier. And then you're going to kick yourself in the butt when you realize these have been posted the entire year and you squandered 8 months of this opportunity and you should have been doing this all along. We'll see. Okay. But with that said, what I did not do is I did not print every slide in the notes. There are some things that are simply meant to be visual. There's nothing on that page that you would have written down in your notes, and therefore I didn't include the page. Get the idea? Okay, so guys, we're going to get started. And by the way, let me mention to you, because we are all now in possession of these notes, there's amazing research coming out of Stanford, if you care. Guys, really good research that talks about the best way to learn. And the best way to learn is to not just have the notes ahead of time, but what should you be doing with these notes because you have them in your possession? Underlining, highlighting, jotting notes to yourself, circling important ideas. Guys, they've actually proven that that's the best way to learn in a classroom setting is by having the notes and then jotting your notes into the notes. So I would encourage you to do that as we go. Okay, so guys, what are we doing today? What are we doing for the last unit of the year? And guys, it's simply this. We're studying gases. This entire unit is all about gases. Now guys, when we talk about gases, and this is not in your packet, guys, we're talking about these critters, right? Remember that from a long, long time ago? We talked about solids, that their particles just sit there and vibrate. We talked about liquids that are like a mosh pit. And then guys, we talked about these gases that do not have intermolecular forces. Their particles are all spread out. They're running around at hundreds of miles an hour, and they Tazvok. They take on the shape and volume of their container. Well guys, here's the deal. We're going to spend 2 days on this. 2 days of lecture, 3 days of lab, 1 day of video. That's going to be this unit. And guys, I'm just going to be honest with you. It's pretty easy. This is not going to be a unit that you're going to be going, holy smokes, that was really difficult. The thing that's crazy is when you come back to take AP next year, guys, this unit is traditionally the hardest unit we will do. Top 3 anyway. It turns out that we are skimming over some very difficult material. We're going to simplify this year and then get into the craziness next year. So guys, do you have sort of a mental picture for what gases look like? You okay? So guys, now here's what I want you to do in your brain. You ready? So if this is what gases look like in picture form, what I want you to do is this. In your brain, turn that into a video. You understand what I'm saying? Take that still picture where we understand the gas particles are all spread out. They don't have intermolecular. And guys, if we were to turn this into a video, what would it look like? Absolute chaos, right? But guys, the problem is that we can't show you what it looks like inside of a gas because we can't see the particles. So it turns out there's this physics teacher, I think he's like in Indiana, that in an effort to try to model this for his students, actually built this. And I tried to build it and frankly got frustrated because I couldn't get the plunger to go up and down right. And finally, I just started cussing and gave up. But guys, if you're looking for a mental picture for what a gas looks like, consider this. That's actually a good representation of what is going on inside of a gas. He added a couple bigger gas particles to show that small gas particles, the little metal balls, are actually moving faster than big gas particles. So like if you had helium and neon, the helium would be moving faster than the neon. We talk about that in AP. But guys, this is literally a really good dynamic view of what's going on inside of a gas. These particles are moving at hundreds of miles an hour. This is actually in slow motion. At full speed, it was nauseating. And they're running into each other. They're slamming into the walls. That causes pressure. And that's a really good model of what's going on inside of a gas. You get the idea? Okay, so guys, here's the thing you need to understand. There is a term that we use to describe what's going on inside of the gas. I'm going to use the word with you and then make sure you understand what it means. Guys, this is what we call chaos. Do you know what? That sounds really annoying, doesn't it? So guys, this is what we call chaos. So what does it mean for a system to be chaotic? It doesn't just mean crazy. Does anyone know technically what it means? No? Let me define it for you. It means unpredictable. So guys, when you have a system that is chaotic, it means you cannot predict what it's going to do. So for example, if you were to pick one of these balls, even one of the big balls because they're easier to follow, guys, if you were to pick one of these balls and if you were to hit pause and find the ball and then hit play, there would be no way for you to predict where any of those balls, let alone the big ones, are going to go. That is the definition of chaotic. It is a system that doesn't allow prediction because it's absolutely crazy. Okay, so guys, that brings up a problem, and this is where your notes start. So guys, if you grab this notes page in front of you, do you notice the fourth word that's on the page? Chaotic. Guys, gases are chaotic systems. So now we've got a problem. We understand that gases are chaotic, and chaotic systems do not allow prediction. The problem is this. We've got to figure out how to study them. So guys, the bottom line is because they're chaotic, their behaviors are really complex, and they're hard to describe mathematically, but we need to figure out how to describe them mathematically. So guys, this is the solution. To address this problem, and are you guys seeing this is all in your notes? Okay, so guys, to address this system, what we do is we use this simplified model for gases. So when you hear the word simplified, you think stupid and dumbed down. Guys, that is not what we're talking about here. Scientists do this all the time. In the mind of a scientist, what you're trying to do when you study things is figure out the simplest way to study something. So guys, the idea is this. This could be us, this could be someone with PhDs. We all do this. So when we study gases, because they're chaotic, they're hard to study. So we use simplified models. And guys, these simplified models let us just do easier math. But the thing that's cool is it doesn't change the answers very much. So we've got choices. We can study gases as they really are, crazy complicated and hard to describe, or we can describe gases as they kind of are, a simplified model. The math is easier, but the answers don't change. So what's the obvious choice? Use the simplified model. Does that make sense? So guys, now we're going to talk about the simplified model. This is something you want to underline in your notes because this is wildly important. Guys, this simplified model is what we call the ideal gas model. Now guys, the first thing you've got to understand is this, and it's not in color on your page, but you may want to make it stand out. Guys, these don't exist. There is no such thing as an ideal gas. So why do we talk about them? Because it's easier and just about as good. But guys, fundamentally, ideal gases do not exist. But we use them because it's a useful model. So, guys, what are ideal gases? What are they all about? Now, guys, you don't need to know this in the technical jargon. You need to understand what this means. So, guys, when we talk about ideal gases, here's what we do. We pretend, remember these don't exist, we pretend that gases, the molecules in gases have mass but no volume. Now guys, let's talk about what that means. What does it mean that something has mass? It exists. What does it mean that it has no volume? Doesn't take up space. Is that possible? No. You can't exist and not take up space. But guys, it turns out that the space that the gas molecules occupy makes the math really difficult. So to simplify our model, we say that the molecules exist, but they don't take up space. That's simplification number one. Guys, simplification number two is this. Gases don't have intermolecular forces. Did you underline that? Do you find that troubling? Guys, why is that bullet point troubling? Can any of you back this out? No? Okay. Right, but what have we been saying about gases all along? Remember the slide that was just up a minute ago? Solids, liquids, and gases. What makes gases unique? They don't have intermolecular forces. All throughout the year, you guys have believed that gases don't have intermolecular forces. I was lying to you. Guys, gases actually do have intermolecular forces. It's just that they're very, very weak. Now what we're going to say is this, that gases actually don't have any intermolecular forces. Because remember guys, ideal gases don't really exist. So when we talk about ideal gases, we're going to say that they have zero intermolecular forces. Now guys, up until now, you've believed that that was fully true. Turns out it's not fully true, it's just kind of true, but we're going to pretend that it is all the way true. So guys, we're going to pretend that these gas molecules never stick together no matter what. So guys, this is what we're now saying. You ready? We are saying that gases are complicated. Because they're complicated, we need to find simpler ways to talk about them, but our simpler ways need to provide reasonable answers. And so to get that simpler model, we talk about ideal gases, which really don't exist, but when we talk about ideal gases, we talk about gases that have molecules that are there, but don't take up space and never stick to each other. Are you now glad that I printed the notes for you? You guys okay? Okay, so guys, now that you have a sense of this idea of ideal gases, there's one more thing that we need to add to your understanding of gases before we move on, and that is the concept of STP. Now guys, do you remember when we did the moles unit? Actually, I'm going to write this down. You don't need to write this down. But guys, do you remember when we did the moles unit? And when we were in the middle of that unit, we had, remember this thing? Remember that T-chart? And we had moles right here, and I think this was mass, and I think this was particles. And then we went down here, and this was the volume of a gas. Do you remember what the volume of a mole of gas was? Oh, good for you. It's 22.4 liters. But then do you remember what else it said? You remember it said at STP. You remember that? And then in the problems, it kept saying a gas is so many moles at STP. And you guys came back and you said, what is STP? And I said, don't worry about it. We'll talk about it later. Now's later. We're going to talk about it now. So guys, what does STP stand for? You've got it in your notes. The idea is this. Guys, gases are very responsive to their environments. You squeeze them, you heat them, you cool them, they expand and contract. And so guys, when we say the volume of a gas is 22.4 liters per mole, that can change depending on how hot or cold it is. It can change depending upon the pressure. So in order for us to understand gases, we've got to control those factors, and those factors are temperature and pressure. These are the things that change the way gases behave. So we establish standards. They're called standard temperature and pressure. So guys, first of all, standard temperature. Guys, standard temperature is 0 degrees Celsius or 273 Kelvin. And guys, we're going to talk about the Kelvin temperature scale in just a minute, and then we're going to watch a video on it after the SAGE test is over. But guys, let's put this in context. Is that hot or cold? 0 degrees Celsius. Is that colder or warmer than it is right now outside? It's colder. Guys, what temperature is 0 degrees Celsius? Freezing point of water. You may want to write that down if you didn't know that. Guys, 0 degrees Celsius is the temperature at which water freezes. So it was below 0 degrees Celsius at Brighton last night because they got 6 inches of snow. And they're still open. Not that I think about these things, but okay. So guys, 0 degrees Celsius, but what you're going to find out in a minute is this is the same temperature as 273 Kelvin. So guys, let's talk about this a little bit. First of all, you need to know how to convert, and the equation is really simple. If you're given a temperature in Celsius, like 0, add 273 to it, and that's the same temperature in Kelvin. So guys, where on earth does this idea come from? You don't have this slide, but let's talk. You ready? Guys, it goes like this. Don't try to write it down. You'll understand it quickly. So guys, we actually have 3 temperature scales. We've got Fahrenheit, Celsius, and Kelvin. And then what I've done is I've given you 3 landmark temperatures. The boiling point of water, the freezing point of water, and then absolute zero. So guys, let's remind ourselves, what happens at absolute zero? Nothing, right? You understand that inside a solid, the particles are sitting there and vibrating, but if you cool down the solid, they vibrate more slowly. Well, if you can cool those solids down enough, they reach absolute zero, which is the... Ever been to absolute zero? No. We've been within 1/10,000,000th of a degree. And have we watched that video? I thought so. I think we had a sub that day. But guys, we've been within a 10,000,000,000th of a degree, but we'll never get there. It's impossible. So with that said, guys, let's talk about these temperature scales. So first of all, let's go through the Fahrenheit scale, because that's probably the most familiar to you. So guys, what temperature does water boil at in Fahrenheit at sea level? Do you guys know? 212? Did you know that? Yeah, it's actually 212 degrees. What does it boil? Well, never mind. But it's 212. Do you guys know where that came from? Do you care to know? Let me give you the rest of the scale. Guys, what temperature does water freeze at in Fahrenheit? 32. So guys, this was a scale that was made up by a guy named Lord Fahrenheit. So how did he come up with these numbers? Where did 32 and where did 212 come from? And the answer is they didn't. When Fahrenheit made up his temperature scale, this was about 300 years ago, what he did is he got the lowest temperature and the highest temperature that he could accurately recreate, and he called those 0 and 100. So guys, what did Fahrenheit think the hottest temperature was that he could recreate accurately? Body temperature. So what he did is he called his core temperature, he called that 100 degrees. What do we know it to be? 98.6. So he was close. 300 years ago, that was pretty good. He called it 100. And then, guys, he called the 0 point the lowest temperature that he could create. And so what he did is he made a solution out of ice and water and salt. And you guys know that trick, right? If you make homemade ice cream, you put salt in the ice water, and that makes the ice water colder, which makes your ice cream freeze more quickly. Well, guys, he was able to create this brine solution that was very cold, and he called that 0. So if body temperature is 100 and if salt water is 0, then regular water freezes at 32 and body temperature was 212. Or I'm sorry, boiling water was 212. So that's where it came from. Anyway, so that was a mess. But guys, on this scale, absolute 0 is 459 degrees below 0 Fahrenheit. These are not numbers you need to know. So now let's do Celsius. So guys, what temperature does water boil at in Celsius at sea level? 100. You know that in Utah it's about 96 degrees because we're at a higher altitude. What about the freezing point? That would be 0. Do any of you know absolute 0? It's negative 273. So now, guys, this is the thing that's cool. So what is the Celsius scale based upon? The freezing and boiling point of water. And guys, that's great if you're studying things like water that freezes and boils at temperatures that are sort of comfortable for us. Well, guys, this guy named Kelvin came along, and he decided that he wanted to create a temperature scale that was more useful for doing cold temperature science. In the video you're going to see after the SAGE test, you'll see the work that he did. But guys, this is what Kelvin did. He took the Celsius scale and he moved the 0 point. He said, instead of calling 0 the freezing point of water, let's call the 0 point absolute 0. But he based his scale on the Celsius scale, so degrees Celsius and degrees Kelvin are the same magnitude. So guys, this right here represents 273 degrees, but a Celsius degree is the same as a Kelvin degree, so this also represents 273 degrees. So because that's true, what temperature does water freeze at? 273, and what does it boil at? 373. You get the idea? Okay, so guys, that's the fundamental difference between Celsius and Kelvin. And guys, in this unit, you have to use Kelvin temperatures. So if you're given Celsius temperatures, what do? Add 273, and that's this, okay? And then, guys, we know that at 0 Kelvin, there's 0 movement. The molecules hold still. You guys good there? Okay, now, guys, moving along to standard pressure. Standard pressure is defined as the pressure at sea level on an average day, which is very wishy-washy. That was a little wishy, didn't even mean. Okay, but guys, it is truly an average. So what is that pressure? Well, guys, in units that you're familiar with, it's about 14.5 psi. So when you inflate the tires on your car to 32 psi, that's about double atmospheric pressure. But those aren't the units we're going to use. Guys, the units that we are going to use are atmospheres and kilopascals. So all three of these pressures are the same. So standard pressure is 1 atmosphere or 101.3 kilopascals. Those are just units you need to know. You guys good? All right. So guys, now what we're going to do is we are going to get into the math. Well, sort of. We're going to get into and you're going to need to take notes into your notes. Guys, from here on out, I deleted stuff because I wanted you to write it down. So guys, here's what we know now. We know that gases are very sensitive to changes in temperature and changes in pressure. So now what we're going to do is we're going to talk about how gases respond to changes in temperature and pressure. Now guys, here's the problem. You're going to see, and you can see this in your notes, these are called laws. Charles' law and Boyle's law. And now you're thinking, oh crap, if these things are laws, they've got to be really important. And if they're really important, they've got to be really difficult. Because if it wasn't difficult, they wouldn't call it a law, they just call it common sense, right? Guys, these are all common sense. You already know this stuff. Ready? Charles' law. Watch my hands. Ready? Charles' law goes like this. If this is a balloon and you heat it up, what does it do? Gets bigger. If this is a balloon and you cool it down, what does it do? Gets smaller. You guys understand that, right? You heat up a gas and it gets bigger. You cool down in a gas and it gets smaller. That's Charles' law. Guys, when Charles proposed this 300 years ago, that was a really big idea. For us, it's common sense. So don't overdo this. It's just common sense. You heat up a gas, it gets bigger. You cool down a gas, it gets smaller. You already knew that, but we have to say it like Charles did. Ready? The volume of a gas at constant pressure varies directly with Kelvin temperature. What does that mean? Heat up a gas, it gets bigger. Cool down a gas, it gets smaller. Okay? But guys, the thing you've got to realize is it has to do with Kelvin temperature, and you'll see why in the lab that we're going to do right after the SAGE test. But guys, if you don't understand what we're talking about, this is the idea. Draw the arrows with me. Ready? If we take a gas and heat up the temperature, what happens to its volume? Does it get bigger or smaller? Bigger, so the volume goes up. And guys, what happens if we take a gas and cool it down? Does it get bigger or smaller? See, guys, that's Charles' law. That's not hard. That's common sense. Okay, so guys, let me give you some other examples of this. So I bet you guys have had this experience. For those of you that drive, have you ever gone out on a cold winter day and it looks like your friends pranked you and let the air out of your tires? You ever notice that? Unless you're privileged and park in a garage. But guys, if you have to park your car on the street because your parents don't love you, just kidding. But guys, if you have to park your car out in the cold, pay attention. It's not going to happen until next winter. It doesn't get cold enough. But on a frigid winter day, if your car has been parked outside, look at your tires and they're going to look flat. But guys, it's not because your friends pranked you. What happened? Why did they got cold. And because they got cold, the molecules are moving slower. They come together, and what happens to your tires? They look flat. The volume goes down. But guys, now do this. Then drive to school. And as you drive to school, as your tires roll, that causes friction. Friction causes heat. It heats the gas back up in your tires. And what are they going to look like by the time you get to school? Filled back up. Exactly. So guys, if that helps us understand that cold gets small, what about this? Guys, how do hot air balloons work? Have any of you ever been up in a hot air balloon? Guys, you understand this, right? You know how these work, that there's a big old blast furnace right here. And so, guys, it sounds like you don't know how this works. So, guys, the idea is this. That blast furnace does not cause the balloon to expand. Do you understand that? If it did, the balloon would pop. So, guys, how does a hot air balloon work? Do any of you know? Do you know? That's true. They love to go out in the morning when the air is cold so that there's a greater difference in density. Okay, so the gas inside the balloon gets heated up, so why doesn't the balloon explode? There is. I don't know if you guys know this or not. There is actually a trap door in the top of the balloon. And so anytime the balloon pilot pulls on the burner, he gets Charles' law. He understands that, or she, they understand that as they heat that gas is going to expand. And if it's got nowhere to go, the balloon is going to explode. So as they pull the furnace, they also pull a rope, which literally causes a gaping hole to open up in the top of their balloon. And as they heat the gas, they allow the gas to escape out the hole. And then when they shut off the furnace, they close the hole. And now the gas that's inside that balloon has expanded. It's less dense and the balloon goes up. Guys, if there wasn't a hole in top of the balloon would explode. You get the idea? Okay, so that's Charles' law. So now, guys, let's go on and let's talk about Boyle's law. Ready? Guys, this is also This is also common sense. You ready? So here's Boyle's law in a nutshell. So here I've got a balloon. And imagine that I could take this balloon and that I could give it a big hug from all sides, and if I could squeeze the balloon. And when I squeeze the balloon, what happens to the size of the balloon? Does it get bigger or smaller? It gets smaller, and of course when I do this, it just deforms. But if I squeeze this balloon equally from all sides, if I could go, and if we could all squish this, if we could increase the pressure on it from all sides, the balloon would get smaller. Now guys, obviously I can't do that with my arms, but how could I do that? I could take this thing to the rec center and I could take it to the bottom of a pool. Have any of you had that experience when you dive to the bottom of a pool and it makes your ears hurt? Your ears hurt for the same reason that the balloon gets smaller. There's more pressure at the bottom of the pool, and just like this balloon is getting squished, your eardrums are getting squished, and that hurts. So guys, the idea is this. If you take a balloon and if you increase the pressure on it, what happens to the size of the balloon? Does it get bigger or smaller? It gets smaller. Does that make sense? You increase the pressure, the balloon gets smaller. What if we decrease the pressure on the balloon? It gets bigger. And how could we do that? We could carry this thing to the top of Mount Timpanogos. And if we carried it to the top of Timp, which is about 5,000 feet higher, there's less air pressure up there and the balloon would get bigger. Have you ever had this experience with a bag of Dorito chips going camping? Have you ever had that happen? You take a bag of Dorito chips up into the Uintas and that sucker is going to pop. Have you ever seen that happen? Guys, the idea is that bag of Dorito chips is like a balloon. And when you take that thing up to Mirror Lake, there's less air pressure at Mirror Lake. The pressure goes down and that Doritos bag expands to the point that it's ready to explode. So guys, that is Boyle's law in a nutshell. So let's talk about it. If we increase the pressure, what happens to volume? It goes down. And if we decrease the pressure, what happens to volume? It goes up. And so guys, the way that Boyle said it was this, ready? The volume of a gas at constant temperature varies inversely with pressure. Guys, all that means is it's an opposite relationship. So if the pressure goes up, the volume goes down. And if the pressure goes down, the volume goes up. So guys, let me give you some other real world examples. Ready? What about this? Do you know what this is? It's a weather balloon. And guys, this is actually, if you don't know, these weather balloons are set up to go like 100,000 feet in the air. They send these weather balloons so high in the air that you can actually see the curvature of the earth from up there. It's really cool. But guys, when they launch a weather balloon, this is what they look like. So why didn't they spend the time to fully inflate that balloon? Go ahead, Savannah. Yeah, what's going to happen to it if they fully inflate it and send it up? It's going to explode, right? Because the idea is as we move up in our atmosphere, the pressure goes down, right? That's why water in Utah doesn't boil at 100 Celsius. So as we go up in our atmosphere, the pressure goes down and that balloon's going to expand. And so guys, if they fully inflated that balloon on Earth and then sent it up, it would rise a couple thousand feet, explode, and all their weather instrumentation would crash to the ground. So they send them up partially inflated and then they blow up, not because they're adding gas, but because the pressure is going down as they go up. You get the idea? Okay, so guys, that's it. That is Boyle's law and Charles' law in a nutshell. So now all we've got to do, guys, now that we understand it conceptually, is talk about it mathematically. So guys, this is the equation that you need. Did I give it to you? Is it there? Oh, excuse me, I'm hiccuping. Sorry. Is it there? Okay. So guys, here's what it's saying. This is actually Boyle's law and Charles' law put together. Notice how this works. Boyle's law talks about pressure-volume relationships. Charles' law talks about temperature-volume relationships. And so what do the I's and the V's mean? Well, these mean initial, and these mean F for final. So what you're going to do is you're going to use this equation to figure out what happens to the volume of gases as we're changing the temperature and the pressure. So guys, we're going to solve 3 of these, and then we're going to call it a day. So guys, here we go. You've got the question in front of you, right? Do this with me. Here's what it says. We collect 75 cubic meters of gas at 25 Celsius. What will its volume be at 150? So guys, you've already got this in front of you, so let's talk. Ready? Always do this first. Guys, think before you start doing math. So here's what we know. We know the volume at 25. The question is, what will the volume be at 150? Guys, what's the answer given Charles' law? What's the answer? Bigger. Guys, think. Bigger. Do you get bigger? It's fun to say bigger with the bu. Bigger. Guys, it will get bigger. Why? Well, it's getting hotter. And if it gets hotter, it's going to get bigger. So if we do the math and the answer is smaller than 75, we know we did something wrong. Does that make sense? Okay. So now, guys, how are we going to solve this? Write down the equation first. Do this with me. PI/VI over TI is equal to PF, VF, TF. Always write down the equation first. Now, guys, let's talk. You'll notice what we're given. We're given volume and we're given temperature. What about pressure? Doesn't mention anything about pressure. As a result, we can assume the pressure is not changing. Because we're assuming the pressure is not changing, we can cancel it out. So just cross it off. Then, guys, from there, we just plug in the data that we know, but be careful. So, guys, we need VI. We need the initial volume. What is the initial volume? 75 cubic meters. Now we need to know the temperature. Why is the temperature not 25 degrees Celsius? You got to convert it to Kelvin by adding 273, and it becomes 298. This then equals X. We're solving for our final volume at what temperature? 150 plus 273 is 423. So guys, now it just becomes you and your algebra skills. So the way that I would solve this is take 75, divide it by 298, and multiply it by 423. And then we've got 3, 3, and 3 significant digits. So guys, in the end, we get 2 significant digits. Check your math, and then we'll talk about what I just said, because you shouldn't like it. You guys okay with the math? Can we talk significant digits? Guys, look at your setup. How many significant digits in 75.0? 3, 3, 3. How many are in the answer? Why? The answer is because this number right here, 298 Kelvin, is actually based on 25 Celsius. 25 Celsius is only 2 significant digits. When you convert it to Kelvin, you're not increasing your accuracy. So you only get as many significant digits as were in the original problem, and that would be 2. Does that make sense? All right. So now, guys, let's do another example. Do you have questions? Are you liking having the notes? All right. Let's do another one. We collect 325 milliliters of gas at STP. What is the volume at 760 kilopascals? So guys, on the test, I will not expect you to memorize this equation. I will not expect you to memorize the values for standard temperature and pressure. This is not me going easy on you. They do the same thing on the AP test. On the AP test, they give you an equations and constants sheet. They don't expect you to memorize them, so neither will I. So guys, here's what it says. You collect 325 milliliters of gas at STP. What is the volume at 167 kPa? Guys, before you write, let's think. So ready? We know the pressure is going to go to 167. Where does the pressure start? Standard temperature and pressure. Guys, what is standard pressure? In kPa. 101.3. So guys, think before you write. Watch my hands. The pressure starting at 101.3 is going up to 167. So if the pressure goes up, what will the volume do? It'll go down. Squeezing harder, it'll go down. So our answer, it better be smaller than 325. So let's do the math. Set up the equation. Now guys, what about temperature? What's happening to the temperature? Doesn't tell us. Therefore, we assume that the temperature is constant. Therefore, we can cross it off. So guys, because we get rid of temperature, we just need to plug these in. So guys, what is our initial pressure? What pressure does this gas start at? Standard pressure, which is 101.3. Its volume is 325 milliliters. The final pressure is 167, and then the final volume is our X. So guys, how do we solve this for X? We multiply the left side together and then divide by 167. We've already indicated that the volume should go down from 325. And sure enough, it does. It's 197. Are you good? Okay, so guys, in the first problem, we changed the temperature. In the second problem, we changed the pressure. Guess what we're going to do in the third problem? Both. We're going to change them both. So guys, here we go. Says this: if a gas occupies 3 liters at these conditions, what is the volume of the gas at standard temperature and pressure? So now they give us a pressure and a temperature, and we're going to change both. So you write down the equation. It does not. It can, no, thank you, Isabel. It can be whatever, because we're solving for volumes, so the answer will just be in whatever units the volume started out in. Okay. So guys, we need to know the initial pressure. Well, our initial pressure is 150. Then we need to know the initial volume. That's 3 liters. So 150 kPa, 3 liters. Then we need to know the initial temperature. What mistake are you going to make? Forget to convert to Kelvin, add 273. Then guys, we now need to know the final conditions. What are the final conditions? Standard temperature and pressure. So guys, standard pressure is 101.3 kPa. Standard temperature is 273 Kelvin, like so. And then guys, you'll know that you've done the math properly when you come up with 1.8 liters. So guys, we're going to stop there. You now have 10 minutes. You've got the homework in front of you. I will post the answers to the homework. I haven't done that yet. Frankly, I forgot. But guys, we will grade this on Friday. If you're going to be gone, you can grade it on Tuesday when you get back. Realize on Friday you will have the entire day to work on Sage Review. And then Tuesday and Thursday of next week, we will do Sage. And then we'll finish up this unit from there. So for those of you that have not yet taken the test, I need you to come and make arrangements. And guys, you've got, 10 minutes to work on the homework.